Javier Sanchez Yamagishi from the University of California, Irvine. Professor Sanchez Yamagishi is an assistant professor of physics who will discuss the Eddleman Quantum Institute at UC Irvine. Feel free to share your slides down.
Yep, sorry, 1 second here.
No problem.
Okay. Hopefully that's working. Oh, I don't know why there's animation there. Okay, can you see my slides?
Yes.
Okay, great. So thank you very much for introduction. So again, yeah, so my name is Javier Sanchez Yamagishi. I'm an assistant professor here at University of California, Irvine. I think, so my presentation is perhaps a little bit different than some of the others in that at UC Irvine, we do not currently have a center, a federally funded quantum center. And so we're a bit more nascent in our efforts. On the other hand, we kind of have a unique situation in that we basically had the benefit of effectively some seed funds that came from a private donor named Roy Eddleman. So hence, that's where the formation of the Eddleman Quantum Institute at University of California, Irvine came from. And so this was a kind of unique opportunity where this philanthropist, Roy Eddleman, he had a strong interest in rare earth metals, okay? And this actually started not as a quantum connection, but a rare earth metal connection. So he had a strong interest in chemistry of rare earth metals, and he got connected with a faculty member at UCI named Bill Evans, who's the director of our Quantum Institute here. So Bill Evans is an expert in the chemistry of rare earth metals. And so that's where that connection came. And then eventually it grew and evolved into a general interest in trying to make some support some research efforts here at UC Irvine. And that grew into the Eddleman Quantum Institute. I do want to emphasize that this has been a growing effort, and in the end it's been made possible by a few donations by Roy Eddleman to kind of get some quantum research going, but also some educational efforts as well. But we're still at a point where we're trying to transition that into a larger, more center level, robust effort. Yes, so maybe I can just say then that the situation at UC Irvine is that we currently have a large number of faculty that do research broadly in the area of quantum sciences, but historically that has been mainly focused on, let's say, traditional hard condensed matter physics and quantum materials, okay, and spintronics. In the chemistry department, we have a lot of strong efforts in computational simulations of quantum systems. So density functional theory, we have Kieran Burke, who did a lot of fundamental developments of density functional theory, and Steve White in the physics department, who did a lot of, invented DMRG, which is a very important method for simulating quantum systems. Okay, but we don't have, let's say, a large strength in quantum information science, quantum controlled systems. And where that has started to change is in some of our junior faculty members. So we have Luis Aldehi in the physics department, who's an expert in quantum materials and quantum optics, Max Arguia, who does growth of quantum materials, and then myself, who I have a background in quantum materials and also quantum sensing. So I just kind of highlight that to say, because I'm kind of curious in other institutions, this balance between junior faculty members like myself, so I'm giving this presentation in lieu of Bill Evans because he was not able to attend today, but having junior faculty leaders who maybe coming out of postdocs that were from traditional quantum information science or quantum sensing type groups, and then trying to lead new center scale efforts at the same time. But so let me say then that the mission statement here, that the goal of the Eddleman Quantum Institute is the goal is to simulate discovering new quantum science phenomena and also develop collaborations and also motivate future generations to study quantum science. Okay, so just a few notes here. So UC Irvine a couple years ago was named the HispanicServing Institution, federally designated, and that's because currently a little over 26.5% of our undergraduate students are Hispanic or Latin. So in addition, just noting that we've received recognition for generally the university's ability to improve the educational student outcomes for Latino students, and also in general being accessible and having doing a lot to improve socioeconomic diversity by taking many students from the local community college system. So that's really a strength of UC Irvine. And that's something that we really want to take advantage of when it comes to trying to improve educational opportunities and access for quantum sciences. That is something that we've recognized on multiple levels, both in the PI level, faculty level, and also the administrative level, that this is an opportunity that we have. At the same time, I put these statistics up, and perhaps many of you can anticipate that the situation in the graduate level, let's say PhD programs of physics, chemistry, et cetera, are nowhere near approaching this level of representation when it comes to Hispanic or Latino students or people of color. So this is, so there is also this motivation to try to see what we can do to bridge from the undergraduate to the graduate level as well. So what are some of the things that we've done? So basically, through this private donation, basically we got two different donations. One was an initial gift of $1.5 million, which mainly went to fund research. That was kind of the initial research effort, going to Professor Bill Evans and some other researchers to support research in rare earth chemistry with a quantum focus. But there was some money for that to start getting educational programs going. And that's kind of really where we started. Our director, Bill Evans, was very motivated to get education going. So where that went to initially was to fund undergraduate research opportunities. Okay, so we were able to place 5 undergraduate students for doing summer research in quantum sciences. And for accomplishing this, we had a big advantage that UCI has a very well-developed summer undergraduate research program. Since then, we were lucky to get a follow-up donation of an additional $1 million, which was endowed to create our first graduate fellowship. So this is the first, fellowship that we've had for PhD students at all in the School of Physical Sciences, and UCI graduate division was willing to match that fellowship for up to 10 years. The end result of which is that we get almost 1.5 years of 1.5 graduate student per year fellowship, which we chose to divide up into little mini fellowships that are which we can cover 1/4 of a student per year among 6 different students. So basically spread the wealth around among many different faculty members doing quantum sciences research. So that was kind of the most substantial aspect of the funding that has really helped us kind of get some initial efforts going. Another thing I want to mention is that we have ongoing efforts to work with bridge programs. So these are programs that are already existing that are work to provide mentorship and bridge undergraduate students studying physics and other physical sciences to graduate school. So there's a chemistry program and also the CalBridge program, which is maybe kind of more unique to California, which is a very special program that grew out of an effort from Cal State Pomona Poly. This is a very interesting program that I want to advertise. I mean, I think it got a lot of initial NSF funding, but I know they're trying to further this program. But this is a program that takes local Cal State universities. These are programs which do not have PhD programs, and they take students, provide them with 2 years of intense mentorship, and then works on getting them into PhD physics programs, for example, at University of California. And so this is a program that we're working with, interfacing with as a way to provide increased access to quantum sciences. Okay, so that's kind of more on like fellowship, supporting research. We've also been making efforts to improve our educational programming, and this has been mainly motivated by the establishment of the Eddleman Quantum Institute initially, but then we realized that this is kind of providing some initial groundwork for trying to get a quantum center here at UC Irvine. What we've been implementing so far is that we've, for 2 years now, run a quantum sciences undergraduate seminar, and this has been joint with chemistry and physics. So perhaps what I should have mentioned earlier is what's unique about perhaps our effort here, UC Irvine, is that we have very strong connections between the physics and chemistry departments. And that's allowed us to naturally have an interdisciplinary approach to this quantum sciences program. And so we have local PIs give lectures under research. And 2021, we were able to have 37 undergraduate students sign up. And then 2022, we had 23 students sign up. Additionally, so one thing kind of a big effort we've been trying to make is seeing what we can do to expose students to quantum sciences education at an earlier point in their undergraduate career. This is kind of one of the challenges and hurdles I'll mention later on. The end result of that has been an attempt to introduce a sophomore level modern physics course that has an emphasis on quantum technology and quantum hardware. And so instead of so students can basically choose a modern physics course, which is either focused on traditional particle physics or on astrophysics, or the idea is that we would have a quantum sciences type course. And this is a course that comes a quarter after the initial traditional modern physics course, which introduces students to special relativity and some basic kind of pivotal modern physics experiments. The other aspect that we're working on is trying to develop a quantum sciences concentration for both physics and chemistry majors. And this has actually already occurred for chemistry majors and will occur in another year for physics. And this basically is going into this, addressing this challenge of how to get students interested in quantum sciences. And first, it requires exposing them to it. And so, as I kind of hinted at, this challenge of students are, if you think about traditional hard condensed matter physics, which is related to quantum sciences research, you're only exposed to this as an undergraduate at UCI, perhaps in your last quarter of your senior year. So you've already, or if you're going to grad school, you probably have already applied to it and accepted a program, and you haven't even been exposed yet to the topics that you'll be doing research in at grad school or even a master's program. So we want to really try to introduce students earlier. And part of this is motivating students by providing them with a package set of courses, a course that requires ideally also new courses as well, that the students can take. The other effort that we've been trying to do in terms of getting funding and also establishing more at the graduate level is through the NSF NRT program. So this is something that we've been making an effort to do, is also create a quantum sciences interdisciplinary PhD program at the graduate level. And this is joint between chemistry and physics. So UCI already has a interdisciplinary PhD program where chemistry students can have advisors in physics, physics can have advisors in chemistry, and we also have joint coursework as well. And so we've been trying to leverage that to create a quantum sciences PhD program that's also interdisciplinary, joint between chemistry and physics. So the hope was that the NSF NRT program would be one way that we would kind of jumpstart that, but that has yet to happen. Okay. Oh, by the way, if there's any questions, please let me know. I'm not, Serena, is there, what time should I be ending at, by the way? Kind of blabbing a lot.
So about, let's see, probably 11:52, because we went over a couple of minutes. Okay, great. All right, so I'll kind of wrap up. Okay, so one thing I do want to mention is, in terms of thinking about developing undergrad quantum sciences education more, and trying to introduce more quantum hardware-based experiments, we've been trying to think of ways to introduce in our advanced lab courses and also our sophomore lab courses, quantum sciences experiments. So this is an effort led by Luis Jauregui, a professor here at UC Irvine, and so two ambitious undergrad students to establish in our advanced physics lab course, which is a course taken by juniors and seniors, physics majors, a lab that allows them to really do a quantum coherent quantum sensing experiment. And so we actually followed this very nice write-up from Wellesley College on how to develop this type of tabletop quantum experiment. So I highly recommend it. It does help if you have someone who has some background in optics to set it up. But this is our kind of first effort from these two undergrad students who in a month were able to build a fluorescence microscope setup, fairly cheap collection of parts. And our next effort and the big challenge is to try to then do a coherent pulse quantum experiment with this setup. And that's kind of what's coming next. So basically introducing microwave engineering into this setup, which we think is a critical part of the quantum sciences education on the hardware side.
Okay, so maybe then I can end here with the challenges and hurdles. So as I mentioned, basically the main thing we're really thinking about a lot is how can we get freshmen and sophomores introduced to quantum sciences early? When it comes to making new courses and also trying to make new types of quantum concentrations for our majors, the big issue is disentangling prerequisites, which I think other people have already mentioned. So how do you, so EECS, they have courses that are would be very natural fits for a quantum sciences concentration for physics majors, but we have to disentangle the prerequisites so that you don't have, we're not doubling the coursework for the students to make that work. So in the electrical engineering department here, there's a quantum computation course that we've recently successfully reduced the prerequisites for so that our physics majors can take it. And we want to continue with those efforts. Another aspect is, I'm teaching our sophomore level lab course right now. And what I'm seeing is that there really is an opportunity there to introduce quantum sciences experiments at this point as a way to teach data analysis, error analysis, but this really requires substantial funding to rehaul the lab equipment to make it possible, because we're talking about lab courses that have we have 100 physics majors taking, and so it's quite a bit of lab equipment that's required to handle that course load, that student load. And then maybe perhaps the last thing is that one aspect of UC Irvine is that we have a lot of new junior faculty who are hired who have quite a bit of expertise in quantum sciences, and but we're all junior faculty members. And so how do you balance leading new types of quantum initiatives while also juggling the responsibilities of being a junior faculty member? So we do also have some great, excellent leadership on the senior faculty level, but let's say, we have a kind of disproportionately large fraction of junior faculty members involved in this as well. And so maybe I'll just end there, and happy to discuss.
Okay, thank you very much. Let's see. I think there are questions in the chat, which I'm looking at now. Yes, I see the name Humberto Munoz. Can you feel free to ask your question?
Yes, I'm a professor from Southern University, and I have a graduate and undergraduate students who are interested in doing research in quantum computing applications. But I'm new actually in this field. I just learning the basics of quantum computing. I would like to offer them some seminar like this seminar that Javier was presenting us. But I'm concerned about the prerequisites for these students, and also what I need to consider before then I develop this seminar. I mean, if there is a need for lab equipment to do this seminar or not, because we don't have those capabilities here at the university.
Yeah. So the seminar is just presentations and discussions by faculty members. We do run it in, there's kind of a half priority, which is just to introduce students to local faculty members at UC Irvine, so that there's some potential that they could do research with them. But in the act of doing that, we do realize that the students have a very strong need for just basic understanding of quantum sciences concepts. All right, so the seminar is actually kind of evolving more into just a course, which is an introduction to, let's say, in my mind, quantum science research or quantum hardware. And so my hope is that that we can develop this into a clear curriculum with maybe a textbook or kind of like some course lecture notes to go along with it, and then maybe also videos as well that we can release to be available for other universities to adopt. Because I think, there's this idea that there's this traditional idea that quantum science concepts are advanced and should be learned at the end of your undergraduate career. But there's this growing idea that that's not true. Actually, if you boil down the most essential concepts of like quantum sciences, let's say for doing a quantum sensing experiment, the math is actually very, very basic. If you're just talking about a two-level system, how it reacts to a magnetic field, that's very basic. And we think that you can teach that at a very early level. Even before students take quantum mechanics. So the prerequisites of this course are none. You only have to take freshman freshman physics courses, because the idea is we also want to just introduce students to the jargon, because all other, like you think of astrophysics, I mean, astronomy, they get introduced to astronomy and concepts very early on. There's freshman seminars, there's sophomore courses, so we need to offer something early on.
Okay, thank you.
Yep.
I would like to have this, if you have for the end of the year, if possible, no? To have this a draft of a document where I can start developing the seminar with my classes and my colleagues.
Yes, for sure. No, that I would love to. Yeah, so I would be happy to provide information. We can exchange later. Yeah.
And on that note, Professor Zhu from Penn State made a nice comment about it being great to have a place to share new lab activities developed for QUIS, so that each school does not have to reinvent the wheel. Do you, or I guess anybody who's connected, know of such a resource?
No,
I assume it might exist. Okay.
I googled I googled quantum sensing undergraduate lab.
Okay.
I also kind of heard through some connections. So
yeah, this is Tom. So Q's team is doing some things with curriculum. I don't know at what level they're doing lab-based stuff. I'm more than happy to talk to anyone. I'll put my name in the chat. I have an extensive amount of information on those. And then also, there's also recent papers that were published that Corey presented. So one of them is the building an undergraduate quantum engineering program. There's an entire section on laboratory exercises, laboratory equipment that's named. That paper is cited by 2 more papers that also Corey showed that also have list of equipment, modules, labs that people can do. So I think that I'll work with the rest of the co-organizers to like package that for everyone. But I'm more than happy if you guys reach out to me. That's something that I do every day.
Hi, this is Dan Blumenthal from UC Santa Barbara. Hey, Thomas, how's it going?
Doing good, Dan.
We have an undergraduate photonics teaching laboratory that we started up during COVID. And we have 4 modules in the teaching laboratory. There's an introductory module, which is 1/4. And then we have 2 quantum modules. So Professor Galen Moody at UC Santa Barbara, that's his lab modules. And these labs are hands-on teaching labs. So if anybody's interested, I can put you in touch with Galen, and then I can also tell you about our undergraduate photonics introductory laboratory also.
I do want to address Tomas's question about rehauling lab equipment. So yeah, this was not, I don't have a specific list here, but I'm specifically talking about education. So hands-on labs that a 100-student class can interact with, let's say in sections that are 20 students, 30 students at a time. And so it requires either, ideally you would have little sets of mini labs at the sophomore level. So that means purchasing about like 20 kits, let's say, or 10 to 20 kits, each of which can cost, anywhere from $500 to $2,000, let's say. That's for some kind of simpler experiments. These NV Center experiments, these are a bit more expensive. They're on the $5,000 to $10,000 range, depending on the kind of capabilities you want to have. And because of that increased price for one setup, it works better in an advanced lab where there's fewer students taking the course and only one group of students at a time is interacting with the setup. So yes. So in terms of, ideally we would like to rehaul everything and make it all quantum, and that would require, I think, on the order of, let's say, hundreds of thousands of dollars if we were to do it at every level.
Right. So Javier, for the 2 options you mentioned, it seems like somewhere between 50K and 250K would be the range of needed investment. That doesn't really strike me as substantial.
Sorry. Yes. In the context, I think of let's say things like the Expand QISE grant and other new opportunities like that. Then yes, that it should be addressed.
The way I see it is actually that is not a substantial amount of funding that would generate tremendous impact. It's something worth keeping in mind, that sometimes a relatively reasonable or small even investment can generate tremendous impact.
Yes, agree completely. I meant substantial from the point of view of previously when it was only department resources that were possible. Yeah.
Understood.
And then, oh yes,
Okay.
Sorry, Emily, I don't know if you were saying something, but.
Oh, I was going to say thanks, that it's probably about time to move on to the next session. But if you had a few comments, you have a 1-minute comment that you wanted to make?
My comment was more to Emily Edwards' question about cryostats and lasers. And yes, that's a big issue. And basically, we've only been considering experiments where it doesn't require something very expensive like a cryostat or very fancy laser. So that limits the types of experiments we can do. But I think that is better to have cheaper experiments that a lot more students can have access to.
Yeah, for our lab course, we got a cryostat that goes down to 4K for about Gifford McMahon cryo cooler. It was 20 to maybe it was 30,000, including the turbo pump. So it's not too bad. I think the key is just like being creative about how to rotate students through like one setup, since we can't get a ton of these setups, but it's not that bad.
Right.
Adding a magnet, of course, then it becomes a lot more expensive. Okay, thank you very much. Let's now move on to the next.